This is the 21st lecture of the course, MTH 204A for section B. So, as I have announced in the last lecture that we will be discussing automorphism groups of the symmetric groups. So, as usual, let n be a natural number greater or equal to 3. We wish to show that automorphism this is isomorphic to Sn for every n not equal to 6, and for n equal to 6 z modulo 2z. So, these are the two results we will show. And in fact, we also proved that Sn is as a natural embedding inside odd Sn by means of like Sn is isomorphic to in Sn, which is a subgroup of odd Sn. Okay. And then in order to show this, we first need the following observation. Maybe we can write it as a proposition. So, let phi be an automorphism of Sn such that it takes transpositions to transpositions, that is for every I not equal to j phi of ij. So, the image of a transposition is a transposition. Suppose this happens, then we will show that phi is inner. Okay. All right. So, before we start the proof, let us observe the following thing, that suppose we are given disjoint transpositions for tau 1 up to tau k, and we take their product. So, this permutation has order 2, therefore, when we apply tau on that, the tau of this is again going to have order 2. Okay. And from the cyclic decomposition of a permutation, it is quite clear that in a cycle decomposition there cannot be any cycle whose length is bigger than 2, because in the cyclic decomposition if we take the lengths of the cycles appearing there, and their LCM is going to be the order of the permutation. So, therefore, it is quite clear that it is also going to be a product of disjoint transpositions. And furthermore, we should also observe something, that let us say, let me put it in this way, that suppose this is A prime B prime, and let us say CD, another transposition is some C prime D prime. Now, the question is, if these two transpositions are disjoint, then can we have a common so if these two are disjoint, can we say that these two also have to be disjoint? Yes, that is always the case, because if they are not disjoint, then this is going to be some 3 cycle, okay, whereas their product is going to have order 2. So, permutation of order 2 cannot be moved, cannot be mapped to a 3 cycle, okay, because the orders have to be same. So, thus it shows that if these two are disjoint, these two have to be disjoint, and similarly you see the vice versa, that is if there is anything common here, then this one will be their product will be a 3 cycle. So, its image must be a 3 cycle. So, here they have to be disjoint. So, therefore, 2 transpositions, let us say tau 1 and tau 2, they are disjoint if and only if under this phi tau 1 and phi tau 2, they are disjoint. That is all we observe here. Now, this observation is going to be crucial in this proof. So, what about phi 1 2? Let this be A1 A2. Next we look at phi 2 3 it is also going to be a 3 cycle, it is also going to be a transposition. So, one of them will be common in the, this transposition and this one, they cannot be disjoint, so one of them will be a common. So, by relabeling we can assume A2 is the common one, and certainly this one cannot be A1, so it will be something else. Okay. Next, what about 3, 4? So, again with 3, 4, so the argument is goes in the exact similar line. So, 3, 4 and 2, 3. So, this cannot be entirely disjoint with that. So, there will be something in common. So, can A2 be common here? Can A2 be the common element? Certainly not, because these two are disjoint, hence their image have to be disjoint. So, A2 cannot appear here, it has to be A3, and once A3 is there, then again A2 cannot appear here because these two are different, and A1 cannot appear here because the image of these two have to be disjoint. So, there has to be some another A4. Okay. So, we can continue along that line, and let us say we n minus 1 n, this is some n minus 1 n. The main point is this A1 up to an, they are all disjoint, and they are also from they are nothing but, these AIs are also from the same set 1 up to n. So, thus A1 up to n are nothing but precisely on 1 up to n's. Okay. So, now we define this by tau I equal to AI. Okay. So, since AI is not equal to Aj when I not equal to j, therefore, this belongs to Sn. Now, the way things have done is tau. So, now let us see that hence fine. So, now let us see that tau of 1 2 is phi of 1 2 is nothing but tau 1 2 tau inverse. In particular, for any I to I plus 1, this is what we see, okay, for every I. Now, the conclusion is immediate, because this set generates. Okay. So, what we have obtained here is that this inner automorphism by tau and this phi, they agree at every point of the generating set. We have two homomorphisms which agree at every point of a generating set. Therefore, this forces phi to be the inner automorphism by tau. So, that is how we prove that if our transposition is, if our automorphism takes transpositions to transpositions, then it has to be inner. So, with the help of this, we will prove here that when n not equal to 6, then any automorphism must send each and every transposition to transpositions. That is all we will show. When n not equal to 6, then in view of this proposition, it becomes automatic that every automorphism will be inner. Okay. So, therefore, let us get into this. Let me put it as one of the main theorem. So, it is more like a general observation regarding conjugacy classes. So, it says that, so first assume n not equal to 6. It says that if a conjugacy class in Sn consists of precise exactly NC2 number of elements of order 2 then it must contain a transposition. So, if a conjugacy class contains a transposition, then it must contain all transpositions equivalently. So, contains a transposition equivalently all transpositions. Okay. That is quite clear. So, let me again explain the statement of the theorem. It says that suppose we are having a conjugacy class inside Sn such that the class has exactly this many number of elements of order 2. So, again in a conjugacy class all the elements will have same order, right. So, therefore, from this one can immediately conclude that this is the size of the class, right. This is exactly the size of the class and yeah. So, this is exactly the size of the class because all elements of in that class are having order 2. Okay. So, can we think of one such class, that is a class having these many elements? Of course, like if we start with this transposition 1 2. So, we have how many transpositions do we have in Sn? NC2, right. So, I mean if we start with so the conjugacy class of this has order NC2. Okay. Okay. So, now what we are going to see is that this is the only conjugacy class, with this order, okay, with the only class with this order and of course conjugacy is only conjugacy class having all elements of order 2 and with this size. So, that is the conclusion of the theorem. Okay. So, how to prove that? Okay. So, let us start. So, suppose so pick an element from that conjugacy class. Okay. So, it will be the so since this has order 2, so if let sigma be an element from the conjugacy class. So, since sigma has order 2, so sigma will be some number of disjoint transpositions. So, let sigma assume that suppose sigma is the product of well, so let me here denote this by C, the product of k disjoint transpositions okay. So, here k is of course greater or equal to 1. Suppose sigma is the product of k disjoint transpositions, then the class of sigma inside Sn will contain will be the collection of precisely all permutations which are products of disjoint k number of disjoint transpositions, right. Because in a conjugacy class we always have the permutations having the same cycle type. So, therefore, this contains all permutations which are the product of k number of disjoint transpositions. So, therefore, we are trying to see that this is exactly C, because I mean to begin with C was the conjugacy class of sigma. So, therefore, C contains all permutations of this above type. Okay. So, the question is, what about this? Okay. So, like therefore, you see that like a sigma. So, a typical transposition in this class looks like this, that we have k number of transpositions and then there will be fixed points which you do omit. So, like what is the number of choice for the first transposition? It is exactly NC2, right. Once this is chosen, then we have, so how many ways we can choose this transposition? N minus 2, 2. Similarly, here we can be up to n minus 2k plus 2 by 2. And since they are disjoint, I can shuffle these transpositions among themselves in every possible way. I am allowed to do that. So, therefore, number of disjoint transpositions. Therefore, we see that this, that is number of permutations which are disjoint transpositions of, which are products of so k many disjoint transpositions, the number is exactly this but divided by k factorial. Okay. So, this is a general observation. Here we do not need n not equal to 6 or anything. This is a very general observation. In fact, if you wish, you can put it as a separate lemma. That is not a problem. So, even to come up to this point, we haven't we don't need we haven't even used this assumption. Okay, all that what we have used is like if there is a so if a conjugacy class has, I mean what we have actually proved is the conjugacy class with this cycle type is having size this. Okay, it's a very general statement. So, as I said that if you wish, you can put it as a lemma. But so actually we need this counting formula, we need this commutator formula to deal with this situation, only. So, therefore, I have done it here. Okay. So, by assumption this quantity is NC2, therefore, what you get is n into n minus 1 by 2 in one hand, and on the other hand you have 2 so this is the situation. Then some terms will be cancelled out, then what do you get automatically? N minus 2 factorial. So, here if these two terms get so okay, so let me first simplify this side, n factorial divided by of course 2 to the power k, we have k many terms, and so this factor will be here, then 2 to the power k, then of course we can do this manipulation n minus 2k. Okay. So, and this is n into n minus 1 by 2, and this further implies n minus 2 factorial is 2 to the power k minus 1 times k factorial into n minus 2k factorial. Okay. So, if this happens, then this we must have this. Okay. So, we are now going to show that when n not equal to 6, then this cannot happen if this cannot happen if k is bigger than 1. Okay. So, k1 means there is a transposition. Okay. So, we note the following, that so it is a direct verification that if k is 1, so just look at this formula, we are making observations from that. If k is 1, then so we call this formula star holds. If k is 1, then star holds. Holds for all n. Okay. So, this is one observation, that is obvious. Now, another observation, though like in the hypothesis it is included that n not equal to 6. However, if we just focus, just restrict our attention to this formula and treat this as a independent formula, then we see that this formula holds when n equal to 6 and k equal to 3. Okay, holds for star holds. So, do not get confused. Again, I am telling you that in our assumption hypothesis n not equal to 6 is assumed, right. But however, if we just stick to this, consider this as an independent formula and ask when this holds or not. So, you see in this case it holds, and I leave it a direct verification that. So, it is a direct verification because only a few choices will be left, that if n is less or equal to 5, then star never happens. Then star does not hold. For all k. So, k is bigger, of course, k has to be bigger than 1, because if k is 1, then always it shows k bigger than 1, and this one has to be okay. So, k bigger than 1, I think here the only possibility will be I think 2 would be enough. Yeah. So, so if n less or equal to 5 does not hold when if we put when k is 2, okay, for k is 2. Okay. So, therefore, like when n or like if when n is less than 6, then certainly we do not have any chance to have this formula with k greater than 1. And now what we will show is like the complementary case, that is when n is bigger than at least 7, then still it is not possible. So, therefore, that will finish the proof of this theorem. I repeat, here we have just shown that when n is at most 5, then this formula does not hold if k greater than 1. Next we see that when n is bigger than or equal to 7, then this then also this formula does not hold for k greater than 1. So, thus we prove this theorem, that is when n is anything other than when n is anything other than 6, then the conjugacy class of cycle type of this cycle type. So, the conjugacy class where the conjugacy class consisting of permutations of this cycle type with k greater than 1, they have size, they cannot have this size. Okay. That is what we have proved, or in other words, the conjugacy class of this cycle type when k greater than of this cycle type where of this cycle type with k greater than 1, such a conjugacy class will always have different size, will always have size not equal to that of the conjugacy class of a single transposition. Okay. All right, let me prove it. Once that is there, then this shows that this shows that the only conjugacy class of this size, of course with order 2, the only conjugacy class having all elements of order 2 and of this size will be the conjugacy class of all transpositions. Okay. All right. So, let me get into that. So, what we are going to show is, so here things are slightly like manipulative, we have to be somewhat careful. So, for all n greater or equal to 7 and k greater or equal to 2. Okay, so let me put it in this way, on greater or equal to 7 one has, so this is the statement which we will be proving, n minus 2 factorial strictly greater than k into k factorial into 2 to the power k minus 1 n minus 2k factorial whenever k is greater or equal to 2 and 2k is less or equal to n. Okay. This is what we will prove, that is this side is strictly bigger than. So, if k is bigger than 1, then for all n greater or equal to 7 this side is strictly bigger than that. That is all we are going to prove now. Okay. So, again let me remind you, if we can settle this, then thus we settle that for every, if n greater or equal to 7, then there cannot exist any conjugacy class of cycle of k cycle type of this cycle type where k is strictly bigger than 1 and having exactly this size. K cycle type. Okay. So, this is to be proved in two ways. So, the induction argument is slightly delicate. So, it will be proved in two steps. So, I first talk about the step 1. So, in the step 1 we show that for every k greater or equal to 4, for every k greater or equal to 4, we have n minus 2 factorial greater than 2 to the power k minus 1 into k factorial, where n is 2k. Okay, since this has to be greater or equal to 8 actually. So, first we will show this by induction on k, right. So, therefore, if we can, therefore, in this step what we have shown is we proved this for every n even. Okay, we proved this for every n even. All right. Well, not only just even, like also, yeah. So we, yeah. So what we do is that we prove this statement for every n, of course, even, and exactly and exactly their k has to be half of n. Yeah. So basically this statement settles this. I mean this is nothing but a this is nothing but a partial so it's a partial result for this. Anyway, let's do that. So here we only cover only those n's which are of the form 2k and so that's what I was saying, that once we can settle this, then thus we prove this inequality for even, for all even with k in half of that n. Okay. Okay. So so this is just a, I mean so this is just, I would say, a partial progress in order partial progress towards proving this. So this is just, yeah. So it's this is the, so this is the partial progress in order to prove this. Now first let me prove this. So this is what we will be proving by induction. The base case when k is 4, that I am leaving it to you. This is just a checking. The rest is I will just show you that how to prove this inequality for k plus 1, assuming that this holds for k. That's the main part. So for k plus 1, the observation is, so 2 into k. So we assume this statement holds for k. So what is this? So this is nothing but 2k factorial. Okay. So 2k factorial is 2k, 2k minus 1 and 2k minus 2 all right, 2k minus 2 factorial. We have assumed that this statement holds for k, so and n is 2k, so 2k minus 2 factorial is there, hence we can simply, so to this 2k minus 2 factorial is to the power k minus 1 k factorial, and yeah, so it's bigger than that. Now you can immediately see, so so here we get to the power k, here we get k plus 1 factorial, right, and yeah, so this has to be this, because since k is at least 4, so this is going to be at least 7, right, 2k minus 1, so strictly bigger than 1, so this holds. So once we assume this for n, then from assume this for k, then we know how to show it for k plus 1. So the partial progress we have made. Now let's come to the second part, second step, where we in fact use this partial result. So remember that our aim is to show that thing. Now the rest again is it is just a simple manipulation. So now with step 2 we show that. Step 2 we show that for every n greater or equal to 7, one has n minus 2 factorial bigger than to the power k minus 1 k factorial n minus 2k factorial whenever of course we have n is greater than 2k is greater or equal to 4, that is k is at least 2. In fact, yeah, so k is at least 2. So this is what we will be proving now. Now then we realize that with this, once we prove, already we have settled this, and once we settle that, then together and coupling these two, we obtain this. Okay, coupling these two, we obtain this, because when n equal to exactly 2k, that case has already been taken care of. Okay, so how to do this? So here the proof also, like I am leaving the base case for you to check, that is when n is equal to 7. That's not n is equal to 7, then you have only a few choices left for k. There you simply check. It's not a big deal. Now now let me show you that how to say, if we assume this statement for n, then how we can establish that for n plus 1. How to establish inequality for n plus 1, and for that we let's assume that let k be such that 2k is less than n plus 1. Okay, then we can have exactly two possibilities, either n is 2k or n is even greater than 2k. Okay, so in order to deal with this n equal to 2k case, we used this. So observe the following, that n minus 1 factorial, because you have to prove this for n plus 1, this is n minus 1 into n minus 2 factorial strictly bigger than n minus 1 to the power k minus 1 k factorial. That's exactly due to this, right? And then the rest is quite obvious, because n minus 1 you see is n minus 1 is always greater than 1, because n is quite large, and also furthermore that in order to use this previous thing, you have to ensure that k is at least 4. Here it has to be there, because we are assuming n equal to 2k and n is at least 7. So if n is at least 7 and even, then n has to be at least 8. Okay, so we can perfectly apply the previous argument. So this is nothing but to the power k minus 1 times k factorial. Thus we are already done. So when n is 2k, in this case we have established this inequality, and when n is greater than 2k, so this is let me n equal to 2k case, Now let us do the other case, n greater than 2k, n strictly greater than 2k. There also it is not difficult. N minus 1, n minus 2 factorial, which is strictly bigger than n minus 1, of course. Now since n is greater than 2k, we use induction hypothesis to the power k minus 1, k times n minus 2k, right, and the rest is again another quick manipulation. So this already n minus 2k factorial is there. Now n minus 1 is certainly bigger than n minus 2k plus 1 because k is so huge. So therefore n minus 2k plus 1 into n minus 2k factorial. Okay. So this is exactly what you want. That is, this is n plus 1 minus 2k factorial, that is what you want here. Okay. So thus in 2 steps we establish this formula. Therefore you see that the relation, like the initially the observation that we made, that if a conjugacy class consists of all permutations of k cycle type, all permutations of which are disjoint products of which are products of disjoint k cycles, if such a conjugacy class has size nc2, then this must happen, okay, and then we show that for all n not equal to 6 this cannot hold if for all n not equal to 6 this cannot hold if k is at least 2. That is all we have proved. Therefore when n not equal to 6, we see that the only conjugacy class consisting of all permutations which are products of k number of disjoint transpositions, the only conjugacy class with the permutations of this cycle type and having size nc2 is the conjugacy class of all transpositions. Okay, that is all we have proved. Therefore, yeah. So that proves the theorem that we have, that proves the desired theorem. Now, okay, because we see that when k is greater or equal to, for all n not equal to 6, if k is greater or equal to 2, then such a conjugacy class where such a conjugacy class which consists of all disjoint, all permutations which are disjoint, all permutations which are products of k number of disjoint transpositions, its size is certainly different from that of the conjugacy class of all transpositions. Okay. So I think I have repeated it enough number of times so that it becomes clear to you what we are actually doing. Now we come to our main theorem. If n not equal to 6, if let, then phi must be. So how to prove that? So proof is actually quite immediate here. So suppose so consider how do we show that? We show that we claim that phi sends transpositions to transpositions. If not, that means there is a transposition. So if not, then there exists transposition tau, or maybe I can write it like this, such that tau AB, so it is going to have order 2, right? It is the product of k number of disjoint transpositions where k is bigger than 1. Okay. Now, since phi is an automorphism, so anything which is conjugate to anything which lies in the conjugacy class of AB, that goes to the conjugacy class of this. Okay. Therefore, the whole conjugacy class of this transposition, the whole conjugacy class of this transposition goes to the conjugacy class of all permutations, conjugacy class consisting of all permutations which are product of k number of disjoint transpositions. Okay. So, this whole conjugacy class goes to that conjugacy class under that automorphism, but just now we have proved they cannot, this is not possible because they are having different sizes. So, therefore, this is a contradiction. Hence, this has to be a transposition. So, yeah, so this is a contradiction that shows that every transposition must go to some transposition by phi. So, in view of the previous proposition, it proves this is inner. Okay. All right. Of course, at this point it is very natural to ask that what happens if we consider An instead of Sn, like the automorphism groups of An, but for that we need to do more work. I can briefly tell you that consider any permutation from Sn, and then since An is normal, if we conjugate An with that permutation, that gives an automorphism of An. So, therefore, thus corresponding to every permutation of Sn, you get a unique automorphism of An. So, then you can show that no two, you can show that this no two permutation of Sn gives the same automorphism of An. That is not difficult to show. Therefore, Sn is embedded inside the natural the automorphism group of An, but however, to show they are equal, that one needs to do more work, which perhaps if you are interested, you can pursue that on your own, but maybe that's we can skip that in this course because we have to also talk about other stuff. Okay. Yeah, but so okay, I think I have left. I have still one more things to say because what we have so what we have just proved is automorphism of Sn is isomorphic to Sn when n not equal to 6. So, we have to talk about what happens with n equal to 6. So, when n equal to 6, first of all, if you recall that in one of the earlier assignments, we have constructed an automorphism of Sn which is not inner. Okay. So, therefore, all right. So, first of all, this is an easy trivial verification that in Sn is a normal subgroup of odd Sn. Okay. That you can immediately check. So, yeah, once this is the case, so this you can check, that is not at all difficult, that yeah, in Sn, so normal subgroup of odd Sn. So, routine verification. So, it makes sense to talk about this, and we have already shown that in one of the assignments that this group is non-trivial. Now, the thing is what can we say about this group? So, that is also quite obvious. Let me see this. So, suppose phi and phi prime are two automorphisms of S6. Yes, so well. This is when n not equal to 6, this is trivial. So, we want to know what happens with n equal to 6, but however, this is always true in general, are two automorphisms of S6 which are not inner. Okay. So, Then what are the possibilities? Let us start with 1, 2. So, like what will be phi of 1, 2? Phi of 1, 2 must have cycle type 3, 2, 2, 2, right? If phi of 1, 2 is, a transposition, then you see that this phi, so the image of every transposition will be a transposition, therefore it will be inner, okay. So therefore thus, so basically we have two conjugacy classes. So let C1, let me write it that let C1 denote the conjugacy class of 1, 2 inside Sn, and C2 conjugacy class of the other conjugacy class, where this 2, 2, 2, 1, 2, 3, 4, 5, 6, okay. So you see that if phi is not inner, then phi must send C1 to C2, right. If phi is not inner, the similar argument goes for phi 2 as well, okay, so for phi prime as well, right. Therefore phi 1 inverse, phi prime inverse phi, so this must send, so this sends, so like this is also for automorphism vice versa. So phi sends C1 to C2, phi prime inverse sends C2 to C1, so this sends C1 to C1. So thus this is an automorphism which sends every transposition to some transpositions, hence this has to be inner, right. So that means like so that means that every like if we fix an automorphism, so let me introduce a terminology. The automorphisms which are not inner, they are called outer automorphisms. In one of the exercises we have constructed an outer automorphism. So this analysis shows that if alpha is that outer automorphism, then every other outer automorphism must be of this form, I tau. So that is alpha times some inner automorphism, okay. So that immediately forces this has to be z modulo 2z. This immediately forces this has to be the modulo 2z, because this group, this is the only non-identity element in that group, okay. So thus we have the complete classifications of automorphism groups of Sn. Now we should move to something else in the time remaining. So here we have only left this thing that this inner automorphism group is a normal subgroup of aught Sn. That is actually quite easy. All right. So now what we will talk about is that earlier we the simplicity of PSL2F. So for where F is any field, having elements, or to be on the safe side, if you are not familiar with fields having finitely many elements, so you can or number fields, you can simply take F to be Q, R or C, okay. All right. So recall that from now onwards, well, so now onwards we let G to be we let G stand for GLNF or SLNF, GL2F or SL2F. So recall that the Borel subgroup is this A, B, C, D, the matrices of this kind, belonging to G, that is if G is GL2 then it is just upper triangular immutable matrices. If G is SL2 then we will have a further condition AB equal to 1, and then we have this unitary group 1 something 0, okay, this unipotent group. Okay. So, and then we have let this be the matrix observations, in fact a direct verification that BW inverse is precisely the collection of all lower triangular matrices okay. That is actually quite clear, like if you just take the conjugation, or yeah, maybe you can do this, that does not matter, AB 0 D 0 minus 1 1 0. So, yeah, therefore, this was determinant 1 is okay. So, the way you see that W square is minus identity. So, basically the W inverse is minus W, right. So, therefore, 0 1 minus 1 0. Then you can immediately check how it operates. So, first it will be simply A0 and minus B minus D. Now, for when you further do it, you should have that D 0 B minus B A, right? Yeah, D 0 minus B A. So, the upper triangular is being changed to lower triangular. In particular, diagonal entries, like diagonal entries are also being swapped. So, not only this is one observation, another observation I should also record here is, so these we are going to use W inverse, this U W is precisely the matrix of this form. Okay. So, for simplicity let us call this lower triangular group by B prime, and here let us call it U prime. We call that U and U prime, these two generate SL to F. Okay. So, now we directly get into our main theorem, the simplicity. So, let me first prove the following lemma. First, let me prove the following lemma, that in G, so again G means this. Recall also that the center of G, if G is GL2, it is the scalar matrices, and the center of SL2 is plus minus identity. So, in G, the intersection of all conjugates of B is ZG. Okay. So, this is the first thing that we have to prove. So, this is in fact the proof. I would like to leave it as an exercise, because like one thing is immediate. For example, if I conjugate by this W or W inverse, I get lower triangular matrices. So, thus if something lies in the intersection, then it has to be diagonal matrix, that is quite clear, being both upper and lower triangular of size 2 by 2 diagonal matrix. Then you further pick up and another element, I think this one will work. Yeah, I think this one will work, then you can show that diagonal elements have to be same. Okay. So, this is just an exercise. Now, the next thing is, so in this proof G can be both GL2 and SL2. Now, for this proof I restrict myself to only SL2. Okay. the statement says that if H is a normal subgroup of G, then either H is contained inside ZG. So, remember here ZG is nothing but plus minus identity, or it commutes, it contains the commutator subgroup of G. Okay. So, this is what we are going to prove, and what is an immediate corollary to this? The immediate corollary to this is, if I consider G modulo ZG, which is nothing but PSL2F, then any normal in a normal subgroup of this will be either, so in a normal subgroup of this, so how will a typical normal okay, let me do it here. So, like when F is having at least 4 elements, then G prime becomes G itself, right? We have earlier proved that the commutator subgroup of SL2 is SL2 once F has sufficient, at least 4 elements. So, thus what we see that in that case, in fact, this is equivalent to say H has to be whole G. Okay. So, what this theorem say, what this shows that the only normal subgroup containing the center properly has to be the whole G, and that immediately implies that this does not have any subgroup other than the trivial one and the whole group, because if anything is intermediate, then that gives rise to a normal subgroup of G containing this properly. Okay. All right. So, now we should prove this. The proof of this is again not quite difficult. So, like recall that in the Breuer decomposition shows that B is the maximal subgroup of G, right? B is the maximal subgroup of G. Since B is maximal, so HB, H is normal, B, so HB is a subgroup, since then HB is a subgroup of G, since B is maximal, this HB, there are only 2 possibilities, either B or G, right? So, what is the first possibility? HB is equal to B, that shows H is contained inside B, since H is normal, therefore H, like for every G, G inverse has to be inside. I think what was the, yeah. So, the lemma was, yeah. So, this is, so H being this GB G inverse, and then therefore H will be in the intersection of all these. So, that is exactly ZG. So, this possibility is now dealt with. So, we are only left with the other one, where we have G equal to HB. In that case, we can write or BH, whatever you like, BA. So, then this can be written as, so W can be written as H times B, then we should look for W, we should now look for what's our strategy. So, U prime, all right. So, U B inverse. So, what is B? So that is fine. So, therefore, okay. So, U bar being W inverse. Okay. So, W is HB, HBU, B inverse H inverse, and this is again. So, like this you can immediately see that if an upper triangular matrix is being some B inverse. Okay. So, this is just as an B in B, that is somewhat, and let me put it in this way, x y is 0 z, and this we will have the inverse of that. So, the diagonal elements must be x inverse z inverse and something here. So, all total here also we are going to have something like this. So, all total what we have proved is, okay. So, all total proved this, that this is the this everything is inside HU, everything is inside HU, that we can immediately see. HU or UH, that does not matter because H is normal, and so UH contains U and UH contains U prime. So, this forces G has to be equal to UH. Now, the rest is simply one line. So, once that is there, G modulo H is UH modulo H, so which is isomorphic to U modulo U intersection H, but U is abelian. Therefore, this quantity is, this is an abelian group. Okay. Therefore, G modulo H is abelian, hence G prime must be contained in H. That is what we want to prove, and already argued that in the when F is having sufficiently many elements, then this is same as saying H equals to G. So, that shows the only normal subgroup of this are trivial ones and whole PSL2. This proves the simplicity of PSL2. Okay. So, with that I will finish this lecture.